Algebra 1 Unit 5, Lesson 2, Part 2, Special Linear Functions, Arithmetic Sequences. In this lesson, we want to identify and use both recursive and explicit formulas for arithmetic sequences and graph arithmetic sequences as linear functions and use those in applications. So an arithmetic sequence, a sequence, of course, is just a list of numbers in a certain order. And it's in this section because if we were to graph them in their order, they form points on a line. So if we have various numbers in an order, each element is called a term in that sequence. So there's the first term, that's the first number, the second term is the second number, and so on. It's called an arithmetic sequence because the sequence in which the difference between two numbers is always the same, meaning to move from one number to another in that sequence, we're either going to add or subtract the same number each time. The number that's added or subtracted each time is called the common difference d. The nth term can be written in two different ways. We can write it in function notation. This is, of course, the y value, or in sequence notation. This is also the y value. It's just two different ways of writing it. So f of n, or if a of n, if I say f of 1, that means the first term. A of 1 means the first term. If I want the term before the nth one, we would use function notation f of n minus 1 or sequence notation a of n minus 1. So 3 is before 4. So if this were 4, this would be 3. Each term is paired with an order number, so we can consider this as a function. So if I have a list of numbers like right here, this is paired with 1, 2, 3, 4, 5, because this is the first term, the second term, the third term, the fourth term, and the fifth term. So we can call this A1, A2 is 8, A3 is 11, A4 is 14, and A5 is 17. So those are the terms of the sequence. If we want to graph them as ordered pairs, this is the x value and this is the y value. So the order they come in is the x value and the sequence one is the y. So 1, 5, 2, 8, 3, 11, 4, 14, 5, 17 will be the ordered pairs. The common difference, how do we know it's an arithmetic sequence, is because to go from here to here, we're adding 3 each time, so d will be 3. The fourth term, again, is 1, 2, 3, 4. The fourth term, which we write a of 4 is equal to 14, or in function notation, we could write f of 4 is equal to 14. Those mean the same thing. So on this one, I'm using sequence notation. This is function notation. If I want to write it as a function and graph it, what would we have? Again, the first term, a1 equals 5, mean it's in the order of 1 and the term is 5. We graph 1, 5. The second one, 2, is 8, so we graph 2, 8. The third one is 11, so we graph 3, 11. The fourth one is 14, so we put 4, 14. And the fifth one is 17, so we put 5, 17, and then we can graph those. You can pick any scale that will work. Since we have only 5 terms and we go up to 17, I just numbered these from 1 to 20, but I only put every fifth one. And then here I skipped 2 squares to show me 5 terms. The first term is 5, the second term was 8, the third term was 11, the fourth term was 14, and the fifth term was 17. The related linear equation, well, if we look, we're only going over 1. Even though it's 2 squares, it's only 1 here. We're going over 1 and up 3, so the slope is 3 over 1. By the way, that's just the common difference d, which will always be, so we have f of n is equal to 3n, and then if we were to go backwards, that would intercept here at 2, so 3n plus 2. How can we find the next term in a sequence? We can do it using the recursive formula given below in 2 different forms. So if we want the third term, we take the one before it, which is the second term, and add the common difference to it. We have to be given the first one and then the common difference to get all of the terms, or we have to be given some term, but generally the formula will give me the first term. The same is true in sequence notation. This means to get the nth term, I take the one before it and add that common difference. The disadvantage is we have to know the term right before the one we want. If we want to jump to a term without having to find all the ones between, we can use the explicit formula and the fact that it's the equation of a line in order to jump to the next one. So to get the nth term, we take the first one, and then we'll have to add d n minus 1 times, so we can take n minus 1 times d. So for example, if I have 3, 8, 13, and I want to go from here to here, it's the third term, but I would add 5 2 times. So we add d n minus 1 times to get to the nth term. In sequence notation, again, it means the nth term is, we start at the first term and add d n minus 1 times. If we were to rewrite this and move everything around, we would have d is the slope, and then the y-intercept is f1 minus d. So considering this as an arithmetic sequence, again, how do we know if it's an arithmetic sequence? Because we're adding 6 each time. Find recursive and explicit formulas for the next term, and then find f of 9 using each formula. Since we add 6 to the previous term, as I said, d is equal to 6. The recursive formulas in function notation are, to get the nth term, we take the one before and add 6, where the first term is 5. And in sequence notation, again, we say to get to the nth term, we need the one before, we add 6, and we're starting with 5. To find f of 9 using the recursive formula, well, I have f of 1, f of 2, f of 3, f of 4, and f of 5. So to get to f of 6, I take the one before, which is f of 5, and add 6 to give 35. Then to get f of 7, I need f of 6, which is this 35, and I add 6 to give me 41. To get f of 8, I need the one before it, which is f of 7, and then I add 6 to get 47. And to get f of 9, I take f of 8, which is 47, and add 6 to get 53. For the explicit formula, just knowing that f of 1 is equal to 5 and d equals 6, the formula is f of n, you put the one you start with, which is 5, and then you add 6, n minus 1 times, which is, if I use the distributive property and simplify, I'll get 6n minus 1, which is a linear equation. So we have f of n is equal to 6 minus 1 in function notation, or in sequence notation, a of n is equal to 6n minus 1. So now to get f of 9 using the explicit formula, all we have to do is substitute 9 in that equation. 6 times 9 minus 1 will give us 53, and we don't have to go through that same amount of work. This would be especially useful if we wanted to get to the 50th or the 100. We wouldn't have to find 49 terms before we could find the 50th. Here we can just jump right to that. We might also be given something in word examples. So it said, Cream purchased a bus pass card with 320 points. Each week costs 20 points for unlimited rides. Write the first 5 terms of the sequence showing the points remaining on his card at the end of a week. So we don't start with the 320 because this was the start, but we're recording what he has at the end of the week. So we need to take the 320, and he's spending 20 each week, so we're going down by 20 each week. The first term is actually 300 because that's at the end of the first week, at the end of the second week, at the end of the third week, and so on. To write a recursive formula, again, note that d is minus 20 because we're going down 20 each time. F of 1 is 30, and then to get to the nth term, we take the term before and subtract 20, and we can write that in either form. A of 1 is 30, and then a of n is equal n minus 1 minus 20 in sequence notation. For the explicit formula, again, I'm going to write it in both function and sequence notation. You would generally only be asked for one of them, and then we're going to simplify to a linear form. So again, we start with f of 1 is equal to 30, d is minus 2, so we start with 30, and then we're going to subtract 20, n minus 1 times, which if we multiply the minus 20 times each of these will give us this, and then the 320 we combine, you get 320, we get y is equal to minus 20n. Again, the thing in front of the n will always be d, and then this will be the starting value. In this case, the sequence didn't start there, but those are the number of points we started with at time 0 before we started taking off the points. The same can be done in sequence notation. How many points does he have left by the 10th week? Well, instead of finding the next 4 or 5 terms, now all we have to do is what? Put 10 inside of the explicit formula and solve. He would have 120 points left. How many weeks will it take until he has no points left? Well, no points left, meaning f of n, which is the number of points, is 0. So if we set 0 equal to this in our explicit formula, if we put that equal to 0 and solve for the equation by taking 20n to this side first by adding 20n, we'll get 20n is 320, and then divide both sides by 20 gives us n is equal to 16. So it will take 16 weeks. If we want to graph the arithmetic sequence on its domain, remember we will graph 1, 300, 2, 280, 3, 260, 4, 240, 5, 220. So the first term was 300. The second term was 280. So I've gone up by 100. Each one of these is 20. So this is 20, 40, 60, 80, 100, 120, 140, 160, 180, 200, 220, 240, 260, 280, 300. The first term was 300, the second one was 280, the third one was 260, the fourth one was 240, the third one 220, and we'll see that in terms of the way we put the scale, we're just going down one square and over one each time, of course recognizing that this is really going down 20 and across 1 so that the slope is minus 20. This is the initial amount as an open circle. It's not really a point in the sequence, so I put it there, but again, it's not actually part of our sequence. Our sequence starts with the first term. This really couldn't continue past here because by this time we've run out of money and he can't keep taking off points. This would be the number of weeks until he had no money left. This would be before he started taking off. This is what he had originally as the amount of money.